minute before to start, right? Yeah. And Timur, can we try to make pictures, because some new listeners join us for this second lecture. So can we try?
Let me try.
Hello?
Okay, I'm only asking you to use your camera to show your happy face here, to make a picture just for memory. Yeah, thank you very much. Aida, hi. Yeah, I'm really happy to see you again. Yeah, if it is
Štefan,
possible,
can you...
just for 2 or 3 minutes, just to take a picture.
Štefan, can you please stop sharing your screen at the moment for very short period? And
yeah,
others...
just for two or 3 minutes. Yeah.
And everybody, I ask you to switch on your face cameras. I will remember all of you. Natalia, can you please demonstrate your IT abilities?
One moment.
Okay.
Only
Still
old
we
guys
have
are...
1, 2, 3 minutes. Yeah, okay, good, very nice. Yeah.
I have made a photo, but I need to check that all the eyes are open and all body happy. I think that's okay.
Yes.
Yeah, okay. Usually we are happier. Yeah. Okay, thank you very much. Thank you very much, Natalia, for your assistance. And now let me say that we can start the second lecture of the mini course, which is given by Štefan Gyürki. And so the title of this lecture is given by the first slide. So we can start.
Yes, thank you, Jelena, for the introduction. Last lecture we were talking about permutation groups, and now we will investigate the relation between permutation groups and the invariant relations. So we will go a little bit further. And at the beginning, I would like to tell you that you are welcome to interrupt me if something is not clear, or if I am starting to hurry up, or at any moment you are welcome to interrupt me if something has to be changed, or I am saying maybe not correct things. So don't be afraid. And also, you are welcome to write me email after the lecture, or if there is something for discussion, or in any case. So you are welcome to contact me. Okay, so just a moment. Okay, it works. 2 weeks ago we were talking about permutation groups acting on a ground set omega. Now, if we have a permutation group acting on a set, we can derive many more actions in quite natural ways. For example, if you consider the set of 2 subsets, then you can just a moment. Then you can, oh, this will not work like I would like to. Okay, I'm sorry. So the image of a 2 subset under a permutation G, you can define in natural way that you will map the first element of the set under permutation G and also the second element. So you will get again a 2 subset. So this works perfectly. Your permutation is sending a 2 subset to a 2 subset. Also, in similar fashion, you can derive an action of the permutation group on the ordered pairs of omega, or also on the ordered pairs, but just on those which have different coordinates. So you can have many more actions from the same permutation group, but in a different, I would say, language. Of course, this natural approach can be generalized into k-subsets or k-tuples or points which are k-tuples and the coordinates are different. But for example, you can define new actions. If you have a group of automorphisms of a graph, then, for example, you can take its action on the triangles in the graph or in the paths of a specified length. So you can create many more actions just by thinking which sets can be preserved by the same set, same permutation group. So let's take this permutation group G, which is on abstract level isomorphic to Z2 cross Z2. So in this action, it is acting on the set 1, 2, 3, 4. Now we can consider its action on the two subsets of this set. So it has, of course, for choose 2 equals to 6, two subsets. I will denote them S1, S2, and so on S6. And we can take a look where the elements of the group map these sets. Of course, the identity fixes any of these sets. So this means that the identity generates or inducing a permutation on this new set as an identity on 6 points. Also, you can take the second element of the group and count where goes the set S1. 1 is mapped to 2, 2 is mapped to 1, so the set S1 is preserved by the second element of the group. Also, you can consider the set 1, 3, 1 goes to 2, 3 goes to 4, so your 2 subset 1, 3 goes to the 2 subset 2, 4. This means that the second element maps S2 to S5. So this is displayed here. So the element 1, 2, 3, 4 generates a permutation which can be written as a permutation of degree 6 on the set of points S1 up to S6. And you can finish this table. You will see that this group now is, of course, again, a permutation group, but now it is of degree 6. So in this manner, you defined a new permutation group acting on a new set, which is now the set of 2 subsets of the original ground set omega. It is easy to check that in this manner, you are obtaining a group homomorphism if you take the original element of the group, and now you will see what is the permutation which is induced by that element. And this mapping here defines a group homomorphisms to the full symmetry group of the new set sigma. Now we have to distinguish 2 cases. One case when the kernel of the homomorphisms is trivial. That means that the identity mapping is an image just of the identity element and no others. So these actions are called faithful actions. Otherwise, when there is more than one element mapped into the identity, in that case, the induced action is called non-faithful. I will give you an example. Consider the full group of automorphisms of a square. So you have a graph 1, 2, 3, 4 when the edges of the graphs are the edges displayed here on the picture by black color. One can ask, what is the generated or the induced action on the diagonals of this square? So, for example, the diagonals can be regarded as subsets of the set of vertices of size 2. If you take, for example, the element 1, 2, 3, 4 of the group, this is in fact a rotation, then clearly the green diagonal goes to the red diagonal. So 1, 2, 3, 4 generates a permutation which interchanges A and B. But if you take, for example, a reflection which interchanges vertices 1 and 3 and preserving 2 and 4, then this permutation fixes the diagonal 1, 3, which is called in this A, and also fixes the second one. So I was able to find an element which is pretending or behaving like an identity in this action. So this is exactly how a non-faithful action looks like. So if I will consider all the permutations which are induced by single elements of the group, I will see that there are 4 elements which are preserving the diagonals on the place. So that means the kernel of this induced homomorphism is consisting from 4 elements, of course, from the identity, from the element 1, 3, 2, 4, and also from the reflections along the diagonals. So this is I would say, a typical example for a non-faithful action. Now, we would like to create some kind of bridge between permutation groups and relations. I think everybody knows what a K-area relation is from the basic course of discrete mathematics, but just to recall that the K-area relation phi is a subset of the kth Cartesian product of the ground set omega. By K-rel omega, we will denote the set of all K-area relations on the chosen set omega. And by rel omega, we will denote all relations which have finite arity on the set omega. Also, we will refer to ith coordinate of a k point alpha if alpha has k coordinates and the element A on the position I will be the ith coordinate. So quite natural notation, maybe a little bit unnecessary slide, but for completeness, I think it is good to recall If the coordinates are pairwise distinct in every k point of a relation phi, then we call this k relation as anti-reflexive relation. So the coordinates are pairwise distinct. They are not appearing twice or more times in any of the k points of the relation. As it was mentioned in the introduction, a natural or induced action of permutation can be defined naturally on the k points and also on the k subset. So probably it is not necessary to repeat it. And now we are coming to a very important notion. We are calling a k-ary relation phi invariant with respect to a concrete permutation group J on omega if it is invariant with respect to each permutation G from the permutation group G. That means that each permutation which I have in the group G fixes the relation phi if I am considering it as a set. So the image of the set phi is under each element of the group is phi. And on the other hand, I can ask what are the elements of the full symmetry group on the omega which are preserving a concrete relation phi. And these permutations are called automorphisms of a concrete relation. You probably know this from binary relations because you can imagine binary relation as a graph or digraph. And exactly when we are looking for the full group of automorphisms of a graph, we are looking for the permutations, for all permutations which preserve the binary relation defined by the concrete graph. And by k in the G omega, we will denote the set of all k-ary relations which are invariant with respect to a group. So to a permutation group and the chosen integer k, we can create the set k in G omega, which contains all the relations which are, or all the k relations which are invariant under each permutation of G, or each element of G. And if we take all the positive integers k and make the union of all such k invariant relations, we are obtaining the full set of invariant relations for a permutation group G. And in other way, if I have a relation phi, then I can define the full group of automorphisms of this relation as each permutation G which fixes this single relation, and for a set of relation phi 1 up to phi s, the automorphism group of the set of relations is defined as all the elements of the symmetric groups on omega which preserve each relation separately. So it preserves phi 1, it preserves phi 2, and so on. That means that if you know all the automorphism groups of single relations, then it is enough to take their intersection. And I will give also examples. So let's consider the same group as in example 1, and let's take two binary relations phi1 and phi2. We can display, since we took binary relations, we can display them using diagrams in forms of graphs or digraphs. Now, let us consider whether these relations are preserved by the group G or not. If I'm taking the element 1, 2, then I would like to see whether its images under single elements of the groups are staying in the relation phi1. So of course, identity fixes it, so I'm not escaping from the set phi1. The second element interchanges 1 and 2, so this goes to 2, 1. Fine, it is inside the relation. The third element sends 1, 2 to 3, 4. Again, it is there. And the last element sends 1 to 4 and 2 to 3. So I'm obtaining the pair 4, 3. Of course, I have to check that all the images of 2, 1, 3, 4, and 4, 3 are inside the relation phi1. Again, if we are switching to the language of graphs, then we have to see that if I am taking the identity, of course, the edge set of this graph is preserved. If I am taking the second element 1, 2, which interchanges 1, 2, and 3, 4, then I have to see that this reflection preserves the set of edges. If I am taking 1, 3, and the 2, 4, then again I have to see that the central symmetry preserves the graph or the edge set, and also the last element in fact does the job that interchanges, or it is a kind of reflection which is interchanging the edge 1, 2 with the edge 3, 4. So if I am helping myself to with a picture, then I can easily see that this first relation is clearly a two invariant relation under the group G. Now, if I am making the same job with the relation phi2, then immediately, if I'm trying to map the pair 1, 2 with the second element, I see that the image is 2, 1, and the pair 2, 1 is not inside the relation phi2. So from this, because of this reason, the relation phi2 is not two invariant. So here is the same thing in clear terms written. I hope I'm now not going so fast and the examples were easy to understand. Now, let us take a little bit more complicated example. 2 weeks ago, we were considering the affine general linear group of degree 5. So it consisted of elements which generates bijection on the finite field of order 5. A is non-zero, and A and B are elements of the finite field of order 5. And we have seen that these mappings are generating a group which is called affine general linear group. So now let us define a ternary relation with this property that I am putting into relation phi1 a triple x, y, z if and only if z equals to 2y minus x, of course in the field of order 5. So for example, if x is 1, y is 2, then I can count that z should be 2 times 2 minus 1, that is 3. So the triple 1, 2, 3, for example, is in phi 1. So this relation contains some triples. And now let us consider whether this relation is tree invariant under the group or not. So what happens if I am mapping by an arbitrarily chosen element G the triple x, y, z? Of course, this induces a triple which we can obtain by the manner that we map x, we map y, and we map z under this element G. So we will obtain ax plus b, ay plus b, az plus b. Now we have to check whether this property is preserved by this triple. So I am starting to count. This is y to g, z to g. So I'm counting the difference 2yg minus zg. And after easy algebraic manipulation, I am getting to the conclusion that really this gives me this was x, I'm sorry, that I'm coming to the conclusion that really the image of z is 2 times image of y minus x. So clearly the image is also inside the set phi1. That means that the relation phi1 defined in this manner is clearly tree invariant under the affine linear group of order 20, degree 5. In similar manner, I can define another ternary relation. Say that if I am putting a triple x, y, z into the relation phi2, if x plus y is equals to z in the finite field of order 5. Now, if I will do the same job, I will see that if this relation is true, then if this relation is tree invariant, then I need to have that ax plus b plus ay plus b should equal to az plus b for each x, y, z which are inside the relation phi2. It is easy to find a counterexample which will say that this is not preserved in each case. So for example, if I am choosing x, y to 1, then clearly if I am putting z equals 2, then 1, 1, 2 is in the relation phi2. And if I am mapping it, for example, by the element G, which is defined, which sends x to 1x plus 1, then 1 is sent to 2. The second coordinate is also 2, and the 2 is sent to 1 times 2 plus 1 equals 3. But it is easy to check that 2 plus 2 is not 3 in the finite field of order 5. So in this manner, I can see that the relation phi2 is not tree invariant. Now, on the other hand, it is interesting to determine full automorphism group of a concrete relation. Here, this relation clearly defines, since it is binary, it is defining an ordered square. So the question is the same as to determine the full automorphism group of an oriented square graph. Now we can proceed in a similar manner like in lecture 1. It is easy to see that clearly a rotation generates automorphisms of these relations or the corresponding graph. So definitely I have at least 4 automorphisms which are defined by, which are generated by this rotation. Now I can proceed using the orbit stabilizer lemma. Clearly the element 1 can be mapped into 4 images. So I can consider all the automorphisms which are fixing element 1. Now, if I am fixing element 1, then this means that the pair 1, 2 can be mapped just onto the pair 1, 2. This means that if H is an automorphism fixing element 1, then it has to fix also the element 2. Because otherwise I cannot obtain as an image of 1, 2 a pair which is inside phi. In similar manner, I can see that also by such an automorphism, 4 should be mapped to 4. So the element 4 is also fixed, and so on. After that, it is easy to see that, of course, the element 3 should be also fixed. This means that the automorphisms which are fixing element 1 is just one, the identity. So now I know that the stabilizer is a trivial group, and I know that the image of 1 is a 4-element set, so I can obtain that the full group of automorphism of this relation has size 4. And this proves that I already find the full group of automorphisms for this relation, for this binary relation. I hope this is clear, and probably this was quite easy. Now, in the same fashion like in the first lecture, we can, for the induced actions, also define the corresponding orbits. If we are taking the action on the kth Cartesian product of the set omega, then the orbits of the induced actions are called k orbits. And by the set of all k orbits, that set will be denoted as k orb g omega. I would like to stress that omega, not omega k. So in this case, it is told that I am taking the induced action on omega to the kth power, kth Cartesian power. Of course, again, because of graph theory and because the first probably not so easy case is when k is 2, then you can find much more results for k equals 2 than other case. And probably for this reason, you can find two orbits under a different name in many books. For example, in Dixon Mortimer, you can find the name orbital, and also in many other sources. So if you see orbitals, then you have to think of about two orbits. Now, I'm not going to prove that in similar fashion, then we derived the number of orbits on the set omega. We can count the number of two orbits of a permutation group on the Cartesian, on the second Cartesian product of the set omega. So the only thing that changes that we have to square the number of fixed points by permutation G. So it's a nice exercise for homework to show that in using this, we can count the number of two orbits of a permutation group G. Now, let us take again a group with 4 elements, but now a little bit different. So here it is. And by that formula, we can count the number of its two orbits. So we have to divide by the number of elements of the group. The identity has 4 fixed points. The transpositions 1, 2, and 3, 4 have each 2 fixed points. So I have 2 such permutations, and the last element of the group has no fixed points. So I am obtaining that the number of two orbits of this group is equal to 6. I can write down these 6 two orbits, for example, by considering first the pair 1, 1, and after that I can take all its images, and I will see that the element 1, 1 can be mapped just to the pair 2, 2 or to itself. So the orbital or two orbit containing the pair 1, 1 is of size 2. Similarly, the number of images of the pair 3, 3 is 2, and so on. Maybe a little bit interesting cases are the 5th and the 6th orbit. For example, if I am taking the pair 3, 1, then of course it is fixed by the identity. The element 1, 2 maps 3 to 3, 1 to 2, so I am obtaining this element. The group element 3, 4, transposition 3, 4 sends 3 to 4 and fixes 1, so I am obtaining this pair, and so on. And the last element maps 3, 1 to 4, 2. So after a while, I'm able to find all the two orbits of this quite small group. Now, one has to understand that the k orbits are precisely the minimal k-airy invariant relations of the permutation groups, if I'm taking minimality with respect to inclusion. It is clear on one hand, for the reason that if I am putting into a relation a k-tuple, then of course I have to put into that relation all of its images. Otherwise, it will be not invariant. So with any element, I have to put its k-orbit into the relation. So it is clear that if k-airy relation has to be invariant, then it should be a union of k-orbits. Because with each element, I have to put the full k orbit into that set. That means that the knowledge of the full set of k orbits provides me the knowledge of full set of k invariant relations of a permutation group, and also the number of such k invariant relations. For example, if I am returning back to the previous example, I already seen that which are the 6 two orbits, and now I can obtain other 2 invariant relations just simply by unions of the 2 orbits. So, for example, R1 is obtained as a union of O1 and O2. And how to see that this is really 2 invariant? Of course, these 2 elements will be mapped, will be permuted just among them with using any element of the permutation group G, and also since these are coming from another 2 orbit, then any of the elements of G will map just one to other or preserve them. So really all the 2 invariant relations can be obtained like this. But I'm taking a subset of 2 orbits and making their unions. Now, an important concept is the k-equivalency of permutation group. We are saying that 2 permutation groups J and H, which are acting on the same set, so this is necessary that they are acting on the same set. Otherwise, there is no sense to define k-equivalency of them. So 2 such permutation groups are called k-equivalent if they have the same k-invariant relations. And in such case, we write that with this symbol that J and H are k-equivalent, or when the set omega is clear, then we can omit the symbol omega from both groups. Since we understand that all the k-invariant relations are coming from k-orbit, then we can formulate an equivalent condition that the 2 permutation groups acting on the same set are k-equivalent if and only if they have the same set of k-orbits. For this reason, some of the authors are defining k-equivalency exactly in this manner, that they are saying that 2 permutation groups are k-equivalent whenever they have the same set of k-orbits. Now, let us consider an example. Take the full symmetric group of degree 4 and the alternating group of degree 4. And it is easy to see that both of them are transitive, so one of the 2 orbits for both of them will be the full diagonal orbit, and the full anti-reflexive set of 2 relations or two pairs is the second 2 orbit. So this is easy to check. That means that these 2 groups are 2 equivalent. Now, we can go further. We can ask whether these 2 groups are 3 equivalent. Now, after a while, we can see that if we consider, for example, a triple 1, 2, 3, it is clear that under the group A4, it can have at most 12 images, 12 different images, because the group A4 itself has 12 elements. So the 3 orbit corresponding to or containing element 1, 2, 3 can have length at most 12. On the other hand, if we consider the triple 1, 2, 3 and its images under S4, then it is clear that that 3 orbit will contain 24 elements, because using the elements of group S4, I can write or I can send the triple 1, 2, 3 to any other triple ABC of different symbols, because it is easy to, it is the corresponding permutation will send 1 to A, 2 to B, 3 to C, and 4 to the remaining symbol. And this is clearly a permutation from S4. So in this fashion, I can see that these 2 groups are not 3 equivalent. All right. Now, if we have a permutation group, then we can do the following. We can, for a chosen K, take all the K invariant relations of that group. And after that, to ask, what is the full automorphism group of this set of relations? Of course, these automorphism groups will contain all the elements of G, but maybe it contains something more. And this full group of automorphisms of all K invariant relations for a chosen K will be called the K closure of the permutation group G. And in a special case, when this automorphism group is precisely the initial group G, then we are saying that the permutation group is K closed. Okay, so a few examples. The symmetric group is always 1 closed, because if I am taking a set, for example, 1, 2, up to n, then of course I can make all the permutations which are preserving the 1 relations. So the full symmetric group will be 1 closed, because I cannot have more. I have in the symmetric group all the permutations and I cannot have more. So clearly the symmetric group is 1 closed. On the other hand, if I am taking a transitive permutation group on the set 1 to n, and let's imagine now that G is a proper subgroup of the full symmetric group on the set omega, then clearly the only orbit I have, 1 orbit I have is the full set omega, and we already seen that the automorphism group of this set is the full symmetric group. So in that case, J is a proper subgroup of J1, therefore a transitive permutation group, which is not the full symmetric group, cannot be 1 closed. That means that no transitive proper subgroup can be 1 closed in the symmetric group. I hope this is clear. So this is what concerns K equals 1. So maybe more interesting are the cases where K is a little bit bigger. So let's go back to example 5 and to the group which we already know. And also we know it's 2 orbits. So let us consider the closure of this group, the two closure of this group. The two closure of this group should be an automorphism of the set of automorphisms which preserves all the relations O1, O2, O3, and so on. From the automorphisms of the two-orbit O1, it is clear that O1 will be preserved when 1 is mapped to 2 or 1 is mapped to 1 and also 2 to 1 or 2. So this says us that if I am interchanging 1 with 2 or just preserving 1 and 2, then I can do anything with elements 3 and 4 and the two-orbit O1 will be preserved. Now I can go further and doing the same job with all two orbits. But I already know that clearly the two closure will be an overgroup of the original group G. And this two closure has to preserve all the two invariant relations. That means that it has also to preserve all the two orbits. I already know that if we'll have to work with this automorphism group of a set of relations. So I can write a chain of equations, or I would say maybe subsets. So from this, it is clear that G has to be a subset of the automorphisms which are preserving O1. So now I am coming to an end, because of course the full group G preserves all the two invariant relations, but I obtained that I have a two orbit or a two invariant relation of the group G which contains only the element of G. So this means that the two closure has to be G.
Can I ask a question?
Yes.
You have pointed that two closure is the automorphism group of all the invariant relations. Does it mean that you can change it to O1, O2, O3, and so on? Really, you can replace only two orbits.
Yes, I can prove that I can come to end with with this, that in fact it is enough to consider the two orbits, because all the two invariant relations I'm obtaining are unions of two orbits. So if there is a mapping which there is a permutation which preserves the two orbits, of course it will preserve also the two invariant relations which are containing these two orbits. We will come to the results on theoretical level, which will reveal us more connection between the closure and the orbits and the invariant relations. Okay?
Thank you.
Now, we have seen a group which is too close. Now, maybe it will be interesting to see a group which is not too closed. Consider a ground set with 5 elements. And consider a subset for 5 and its full group of automorphisms. That means that you can interchange 4 and 5 because you are now taking care about the set 4, 5, and you can do anything with the elements 1, 2, 3. So clearly this automorphism group of this set can be obtained as a direct product of the symmetric group on the elements 1, 2, 3 with the symmetric group on the elements on 4 and 5. This means that this automorphism group of that set M is isomorphic to S3 with S2. Now, let us consider a group which contains just the even permutations from G. Of course, this group G had 12 elements, and now we can see that it contains only 6 even permutations, and all these permutations are here. Now, one can notice that the transposition 4, 5 is not in H because it is not even, but it appeared in the group G. Now, if we would like to prove that this group H is not too closed, then we have 2 possibilities. On one hand, we can prove that this element 4, 5, or this transposition 4, 5 is not contained in H, and it preserves the 2 orbits of the group H, because this will clearly mean that I have found an element which is preserving the 2 orbits of H, but it is not in H. That means that the 2 closure should be bigger than the original group. Or I can count the 2 orbits of the group G and to compare with the 2 orbits of H. Now, in both cases, we have to know the 2 orbits of the group H. These 2 orbits can be written or can be displayed using graphs. So this phi1 means that it contains the pairs 1, 1, 2, 2, and 3, 3. So we are putting a loop if 1 is in a relation with 1 or in a pair with 1, and so on. If I have an undirected edges, that means I have both pairs. For example, here the edge 1, 2 means that 1, 2 and 2, 1 is in the same 2 orbit, and so on. So probably it is easy to understand what the graphs mean. Now, if we have these pictures, we can easily see that this transposition 4, 5 is an automorphism of all of these 6 displayed graphs. And this means that our group H is not too closed. On the other hand, if we will proceed using the second way, then one can count the 2 orbits of G and to see that it has 6 2 orbits and precisely the same as the group H had. So here we had a group H which is not too closed. Now we would like to show that this group H is 3 closed. We can proceed by this. Take an element of, or take a triple, for example, 1, 2, 4, and consider its images under H. If you will count, then you will see that really under the 6 elements, these are the images of 1, 2, 4. This means that phi is a 3 orbit in the group H. Now consider the full automorphism group of this concrete ternary relation. Again, we can proceed by orbit stabilizer strategy. We can see that the element 1 can be mapped just to 3 different elements, 1, 2, or 3. So clearly, 1 to the automorphism group is of order 3. Now, we have to consider the automorphisms that are fixing the element 1. If I am fixing element 1, then let's take the element 4 and see where it can to be mapped. If 1 is fixed, then the 2 possibilities are that the triple 1, 2, 4 goes to itself, or it goes to the triple 1, 3, 4, 1, 3, 5. So that means that 4 can go to either 4 or to 5. And for both possibility, I can find a permutation which does exactly the requested job. So this orbit of 4 in the stabilizer of 1 is of length 2. And after that, if 1 and 4 is fixed, it is easy to check that then every other element has to be fixed. This means that this 3 orbit has 6 automorphisms. But if this orbit has just 6 automorphisms, that means that the full group of automorphisms of all 3 orbits cannot have more than 6. And on the other hand, these 6 should be there because the group itself is preserving all of its 3 orbits. So we are coming to the conclusion that this group is 3 closed. I hope everything is clear. Now the results regarding the relations between the k-equivalency, invariant relations, and automorphism groups. Every group G is k-equivalent to its own k-closure. Of course, this can be seen because they necessarily have the same k-orbits and therefore the same k-invariant relations. So this is quite easy to see. After that, if 2 groups J and H have the same k-closure, then H is a subgroup of the k-closure of G, of course, because trivially H is a subgroup of HK and HK is the same as GK. This means that if I am having a k-closed permutation group, then this is the k-closure of many different permutation groups. So this is the largest group having among the permutation groups having the same k-orbits, or the same k-invariant relations. Now, part C is saying that if I am considering the k+1 closure of the group G, then it is a subgroup of the k-closure of G. Moreover, if I am considering the n closure, when n is the degree of the permutation group, then this n closure of G is the same as the original group. This means that each permutation group G is n-closed, where n is the degree of the permutation group. So using these two informations, we can obtain the so-called Valence chain or Valence series. That G is equal to Gn. Gn is a subgroup of Gn minus 1, and so on. And finally, G1 is a subset of subgroup of the full symmetric group. This part has many corollaries. For example, if a group is too closed, that means that all these inequalities are in fact equalities. Because if a group G is too closed, then G2 is equal to G, and hence the group will be 3 closed, 4 closed, and so on. For each bigger k, it will be k closed. Now, the next part of this proposition is known under the name Krasner's first theorem. It says that G is the full automorphism groups of all invariant relations of the original group G, and it is the same as taking the automorphism group of the n invariant relations of G, where n is the degree of the permutation group, and it coincides with the enclosure. Now, maybe one of the most important part of this proposition for us is that if a permutation group is a full automorphism group of a set of L relations, then it is L closed and also K closed for each K which is greater than or equal to L. If we are playing with graphs, then this means that if a permutation group appears as a full automorphism group of a graph, then it is clearly too closed. One has to make a difference between Frucht's theorem for abstract group, which is saying that each abstract group appears as a full group of automorphisms of a graph, but that theorem is considering the abstract groups. Here we are in fact saying that not each permutation group is appearing as a full group of automorphisms of a graph, because not each permutation group is too closed. Of course, this is a consequence of the fact that the same abstract group can be represented in many, many ways as permutation group, in many different kind of actions and degrees and so on. Now, and the last part of the proposition says that if we are interested in the K closure of a group G, then it is enough to consider really the full automorphism groups of the set of K orbits of that group. And as I mentioned in the part C, then that if a permutation group is K closed, then it is of course K closed for each bigger K. So it is interesting to ask what is the smallest K for which a concrete group is K closed. And this K is called the arity of the permutation groups. Now, let's go a step further. We defined already a stabilizer of a point 2 weeks ago, but it is useful to have two more stabilizers in the theory of permutation groups. A pointwise stabilizer of a set delta, where delta is the subset of the ground set omega, is the set of all those elements of G which are fixing each element of delta in that set. On the other hand, the setwise stabilizer contains all the permutations of G which are fixing this setwise. So it is not necessary that each element is fixed inside the set, but the set as a full thing is preserved. And Wieland was one of the pioneers who derived a lot of interesting results concerning this theory, and he proved that if we have some elements of the ground set omega which are pointwise, whose pointwise stabilizer is the identity, and if this set of points contains k-1 elements, then the group is k-closed. I don't know how much time do I have. I'm somewhere in the I'm starting the last third of my talk, so probably it will take 20-30 minutes.
Yeah, it's fine, yeah.
Okay, so we can talk a bit about the proof. So let us consider such k-relations which are obtained in the manner that I am putting the first k-1 coordinates as the points alpha 1 up to alpha k-1, and consider the last coordinate as any element of the set omega, and create the k-orbits under the group G of this concrete element for each x. So in such manner, I am obtaining a few relations depending on x, which are clearly k-orbits of the group G. Now, consider the full automorphism groups that preserve each of the k-orbits phi x for each x. Clearly, the k-closure of the group G is an overgroup of the original group G. And since I am considering just a few k-relations, then clearly the full automorphism groups of these k-relations are overgroup of the k-closure. It can happen that it is the same. It can happen that it contains something bigger, but it is over it. Now, we will be happy if we would be able to show that H is a subgroup of G. To do this, let us consider any element F of the group H. So we know that this element F is an automorphism group, is an automorphism of each of the relations phi x. Now, so for a concretely chosen x, consider the image of this k-tuple under the element f. Clearly, this image will be in the k orbit of that element. So it will be in phi x. And that means that there is an element, say jx, in the group G, which is doing precisely the same job, that it is sending the k-tuple alpha 1 up to alpha k minus 1x to the same element as it is sent by f. And we can do the same thing with another element y from the set omega. After that, it is easy to see that jx times the inverse of jy is stabilizing alpha 1, alpha 2, and so on, alpha k minus 1. And by our assumption, it is the only element identity. So that means that this jx is the same for jy. In fact, this means that it is independent on the choice of x. So I have an element j in the group G, or G in the group G, that behaves similarly or exactly in the same way that the element f. This means that it has to be the element f. So if f is in the group H, then it has to be also, it has to belong also to G. This means that H is a subset of G, and clearly these two groups have to be equal. That means that really here I have equations in both places, and G is equal to H. Now, if you remember what is a regular permutation group, it is such a transitive group that the stabilizer of any element is the identity. Then we have an immediate corollary that any regular permutation group is too closed, because here in the Valence theorem we have a stabilizer of a single element, so K is 2. Now, consider again an example with the affine linear group of degree 5. 2 weeks ago, we have shown that this group is too transitive. From this fact, it is easy to see that the two orbits of this group, it has just two orbits. One is the diagonal relation, and the second is the full anti-reflexive relation. Clearly, the same two orbits belongs to the full symmetric groups of degree 5, and since G is not S5, then it cannot be too closed. Now we will use the Valence theorem to show that this group is 3 closed. In order to do this, in the first step, let us consider the stabilizer of the element 0. 0 is stabilized under some element of the affine linear group when alpha times 0 plus b is equal to 0. This gives us immediately the condition that the element 0 is fixed by those elements of the group which have b as 0. So the fixer of, or the stabilizer of 0 contains the elements t1 0, t2 0, t3 0, t4 0, and so on. Not and so on, because there are no more elements. Now let us consider from this set which are those which are fixing the element 1. If you are considering that 1 times a plus 0 has to go to 1, you immediately obtain that only one of these elements is fixing also the element 1, and this is which sends x to 1 times x plus 0. So x goes to x, and this is the identity. So we find 2 points in the basic set omega that their pointwise stabilizer is trivial. So directly from the Valence theorem, we are having that this group is tree-closed. This slide is maybe a little bit irrelevant, but I intended to show it for those who are who have a deeper interest in permutation groups, because in the theory of permutation group, it is known notion which is called base of a permutation group, and this is such a subset of the ground set omega whose pointwise stabilizer is trivial. So exactly in the Valence theorem can be reformulated in the language of the theory of permutation group using the base. Also, we have several different bases for permutation groups. If we are considering the size of a base, then it is interesting to find the smallest base, and this number for the smallest size of a base is called the base number of a permutation group. So the Valence theorem can be said in this terminology that if a permutation group G has base number B, then it is B plus 1 closed. Also, if the knowledge of base helps us to quickly find a full group of automorphisms, for example, of a graph. If I know a base, then I have to choose the elements of the base in the orbit stabilizer theorem one after other, and I will obtain the requested results for the automorphism group. Okay, last part of my talk concerns the primitivity and the imprimitivity of a group. If you are taking a permutation group, then you can also consider what is happening with the partitions of the ground set. In this part of the talk, we will restrict the permutation groups to be transitive from simple reason, because for intransitive groups, the notion is not so interesting. So let us take a transitive permutation group and take a partition of the ground set omega into M subsets. This partition is called invariant with respect to this permutation group if for each element of the permutation group and each image of the subsets which appears in the partition holds that the image of each subset is some subset from the partition. So now I am allowed to permute or to map one subset to other subset. Okay, clearly each transitive group has two trivial G invariant partitions. First is the partition into singletons, so to the subsets of size 1, And of course, if I am taking omega as one big subset, then clearly it is preserved by each element. And here appears the question that for a given permutation group G, are there any more non-trivial G invariant partitions or not? If yes, then the permutation group is called primitive. Otherwise, it is called imprimitive. Of course, for intransitive group, it is not so interesting because for intransitive group, you can have small blocks just to take the partition into orbits and immediately it will be imprimitive. So that's why the interesting case appears just for the transitive groups. And if the permutation group is imprimitive, then the non-trivial partition, which is invariant under this group, is called an imprimitivity system, and the subsets which appear in that system are called blocks of imprimitivity or imprimitivity blocks of the permutation group J omega. Almost immediately one can see that for each block in this imprimitivity system, it holds that if you take any element of the permutation group, then this element either fixes the full set or it sends to another set from that system. And since we have a partition, this means that the image and the set are disjoint. Again, many authors define imprimitivity or block systems exactly in this manner, that for them block is when this happens. So by transitivity, it is easy to see that if we have an imprimitivity system for a transitive group, then each block has to have the same size, because due to transitivity, you will map each block at some moment to any other block. And since you have a bijection, because the permutation is a bijection, then the size of the set should be preserved. Now, an easy example, consider the octahedron and its full group of automorphisms. It is clear that the full group of automorphisms of this octahedron is transitive because you can rotate, for example, the octahedron in such way that you can map each vertex to any other vertex. Now, if you take the two subsets which are formed by the pairs of vertices which are antipodal, opposite, which are not joined, or in the graph terminology, which are at distance 2, then you are obtaining a non-trivial imprimitivity system. You can see this just simply by geometric reasoning. Now, very interesting proposition, or maybe it should be lemma or a theorem, is saying a close relation between the stabilizers of permutation group and its block and its blocks. A transitive permutation group is primitive if and only if for all alpha from the ground set, the stabilizer of alpha is a maximal subgroup of G. That means that between G alpha and G, there is no subgroup such that it is overgroup of the stabilizer and subgroup of G in other than the trivial ones. Now, we will just sketch the proof, and the proof is goes by contraposition. We will show that the group G is imprimitive if and only if G alpha is not a maximal subgroup of G. So in one direction, if we have an imprimitive group, then there exists a non-trivial block delta in the set omega. That means that delta has at least 2 points, but it doesn't contain all the points of omega. So its size is somewhere between 1 and n, where 1 and n are excluded. So since this happens, we have a partition pi into the blocks of imprimitivity. Now, let us denote by H the setwise stabilizer of this concrete block delta, and take alpha from this block. Then each permutation which is fixing alpha should fix the full block delta, because delta is a block of imprimitivity. So we have that either a permutation fixes the full block or sends it to another block. But here we have the situation that the element alpha is fixed. That means that the full set delta should be fixed, because there is no other possibility. So the setwise stabilizer is clearly an overgroup of the stabilizer of alpha, and since delta contains at least 2 elements, then there exists another element beta different from alpha, and since G is transitive, then I have such an element in the group G that sends alpha to beta. And this element fixes the block delta, but it is not contained in the stabilizer of the element alpha. That means that G alpha is a subgroup and a proper subgroup of G delta. But on the other hand, G delta cannot be the full group G, because G contains such elements that sends delta to another block, because G is transitive. So this means that G delta is a proper subgroup of the original group G. Therefore, G delta is strictly in between G alpha and G. And that means that G alpha cannot be maximal. So if we have imprimitive group, then G alpha cannot be maximal group in it. In the opposite direction, one can proceed in the similar manner, but in this case, one has to consider the element alpha, and if we assume that there is a, if the subgroup H which is strictly in between G alpha and G, then one can show that a set which is the image of alpha under this group H is a block, and it is not the full set omega. So this proves that the group is imprimitive. Now, a direct corollary is that if we have a regular permutation group, then this group is primitive if and only if it has prime degree. Okay, I still need some time, but let's go a bit to pure graph theory. I think almost everybody here knows what is a weakly connected and a strongly connected digraph. Just to mention, just to recall, weakly connected digraph is such a digraph, then if you forget all the orientations of the darts, you are obtaining a connected graph. And the digraph is strongly connected if you have between each pairs of vertices an oriented path which goes from one vertex to the second vertex. So for example, here you have a weakly connected digraph, because if you forget about the darts, then clearly the picture is connected, but it is not strongly connected because there is no paths from C to A if you are considering the orientation. Now, in natural manner, one can in digraphs consider the invalency and outvalency, or maybe in degree and out degree for some of you. The invalency is the number of darts coming to a vertex, so ending in a specified vertex, and by outvalency of a vertex we mean how many darts are going out from that vertex. Now, a nice result is that if we have a digraph which is in a sense regular, that meaning that in each vertex you have the same invalency and the outvalency, then this digraph is strongly connected if and only if it is weakly connected. Proof is very nice. You can find it, for example, in Gotzi Royal, but also you can prove it by yourself, because really it doesn't need any special knowledge. Now, why we are doing this? As we have seen, each two orbit of a transitive permutation group can be represented as a graph or digraph, and since the group is transitive, then this digraphs will have the property that the invalency and outvalency of each vertex is the same. So there is sense to consider whether a two orbit is connected or not, in a sense whether the graph, the corresponding digraph is connected in weak sense. Now, and we are coming to very nice results, which again joins algebra with graph theory. And this theorem or criterion says us that if we have a transitive permutation group, then this group is primitive if and only if each non-diagonal two orbit is connected. That means that if we draw all the graphs corresponding to non-diagonal two orbits, that each of them are connected. If we find a two orbit whose corresponding graph is not connected, then we immediately know that the group is imprimitive. Now I have just the outline of the proof that one has to see that if there is a non-diagonal two orbit such that the graph is disconnected, then you can define a non-trivial equivalence relation on the set omega precisely by the way that those points which are forming connected components will be the parts of the relations, and this happens if and only if this relation forms or this partition forms a non-trivial imprimitivity system, then the group G is imprimitive. So just a few examples to demonstrate this nice criterion. Let us consider the action of the symmetric group of degree 5, but not in its usual action, but on the action on the 2 subsets of the 5-element set. That means that this action will have degree 10 because the 5-element set has 10 2 subsets. And this action has 2 non-diagonal 2 orbits. One of the 2 orbits corresponds to the Petersen graph, and the remaining 2 orbit corresponds to its complement. As we already know that Petersen graph is connected and also its complement, so in this, using this criterion, it is easy to see that the corresponding action of the symmetric group S5 on the set of all 2 subsets is primitive. So usual picture appears here. So if you draw vertices as 2 subsets, then two subsets are joined by an edge when they are disjoint, and otherwise not. Otherwise, they are joined in the complement. So in order to see that this is really a 2 orbit of the mentioned group, one has to see that in S5, you really have an element which sends the pair A, B, C, D to X, Y, U, V if the corresponding letters inside the pairs are different. So this is this can be a nice homework also for you if you cannot see it immediately. And on the last slide, I would like to show an example for a group which is not primitive. Here also we can take an action of degree 6 of the alternating group of 4. So again, not so usual action of A4, but still of small degree. And maybe it is not immediately visible, but the 2 orbits of this group, which are non-diagonal, are these 3 2 orbits, and you can see that the first 2 are connected, but the last one is disconnected, proving that the action of the alternating group is imprimitive in this example. So thank you for your patience and attention. That was all from my side for today. I'm sorry that it took quite a long time.
Okay, thank you very much. Thank you very much for your talk. Are there any questions to Štefan? Well, actually, I would like to mention that on the slides, one of the previous slides, when you consider the Petersen graph as 2 orbits, is it the same as Krasner graph, right? Yeah.
Yes.
Yeah, so exactly the same. So it is another point of view, right? Yeah, we can consider the Petersen graph as a Krasner graph, yeah, and it is the same as a 2-orbit graph, yeah.
Yes, right. And it is same like Johnson graph. So exactly. So really, this is exactly the way how to prove that the symmetric group of degree n, when n is at least 5, is primitive in the action on the 2 subsets.
That's right, yeah.
So this is the smallest case, and yeah, it's nice.
Yeah, it is very nice, yeah. So very nice connections between graphs and groups and properties, yeah, very nice, yeah. Are there any other questions? Well, okay, but last time you gave us the list of exercises. Do you plan to do the same?
If there is interest in this, I can create some list of exercises. Say I will send it to you in 1 or 2 days.
Okay, would be nice. Yeah. Okay, would be nice. Thank you very much. Yeah.
Lena,
yeah.
I have a question to organizers. Do you have some plans about some problem solving or something like that? Really, in Ekaterinburg, we have local problem solving after these lectures. However, possible, it could be nice if we have some common problem solvings.
Oh, really? So in this case, we need to ask Štefan. What do you think? Is it possible to organize something like that?
Yes, I'm open to this this possibility, because really, when I would like to say everything what I am having on the slides, then it can happen that the examples needs more time than just running through.
Okay.
So.
I think that we need to discuss with Štefan what is the best way to organize such kind of session, right? Yeah.
Yes.
Okay. Thank you, Natalia, for your suggestion. Okay. Any other questions to Štefan or to the organizers? Okay, if not, then let us thank Štefan again for a very nice and very interesting and useful lecture. And it is great. Yeah, I do agree. Thank you very much. And next talk will be given in 2 weeks, the same time, the same place. So stay with us. Thank you very much. Yeah, and there are many messages in chat. Thank you very much. So thanks a lot.
I will take.
Yeah. Okay. Thank you. Okay. In 2 weeks, and we will discuss with Štefan the possibility to have some special session with for solving exercises. Right here. Okay. See you in 2 weeks.
See you. Thank you.
Thank you. Bye.
Thank you for coming.
Bye. Okay. Bye.